Hello, here we are once again. It's the physics video lecture. Physics 107B video lecture 6. So what are we doing today? I have some pretty thoroughly written out notes about the Maxwell stress tensor. And this is actually something that works in field theories in general. So this electromagnetic stress tensor that we're going to construct and apply has its analogon in fluid mechanics and also in elasticity theory. So it's a great first introduction to this. So here's how we'll set this up. The problem is about the force. You want to calculate the force on some object. Electromagnetic force on an object. Okay. And let's go ahead and set this up. The example that we're going to do after we've developed the formalism, we'll come back to this example here. It's going to be a uniformly charged sphere. So you've got a uniformly charged sphere. That's a famous Gauss's law type of problem. It's got that linear force law inside. But here we're going to ask, what's the force on the upper hemisphere due to the lower hemisphere? So calculate force on the upper hemisphere due to the lower hemisphere. Due to the lower hemisphere. And you can't use Gauss's law on this one because you're cutting it in half and say it's all uniformly charged, so there's a repulsive force, right? So the bottom half is pushing the upper half in the up direction. Symmetry gives you that if you had oriented this, X, Y, Z like this, it would be the Z direction. But beyond that, well, we're going to see how that's done. So what we do is we set up a general expression based on the field equations for the force, on a unit volume, force per unit volume. And it's going to be a very complicated expression. We find a way to express it in a simpler way. So that's where we're headed. So first of all, we'll just write force and integrate over a volume the electromagnetic force. So we've got E plus B cross B and rho d volume over a volume. Okay. And the next thing we do is we express it in terms of J. So instead of a V, we'll have rho times B is J. So then we'll have density E plus J cross B d tau over the volume. And then eliminate density and J using Maxwell's equations. So next, eliminate rho J using Maxwell equations. And that is going to take us to, what I'll do is I'll write in the result and then I'll put down what was used. Okay. So we're going to end up with the force integral f b tau with f equals epsilon naught divergence of E times E minus E cross curl of B, close parentheses, minus 1 over mu naught B cross curl of B minus epsilon naught d dt E cross B. By the way, this thing we've run into recently. Okay, what did we use for this? Use Faraday. dB dt is equal to minus curl of E, and use E cross B. You just use the basic product rule, okay? dE dt cross B plus E cross dB dt. And Maxwell's equation was also, so yeah, Maxwell's equations and then these things here. So you actually get here pretty quickly, but we're not done. Okay, so we are just putting this in a convenient form. So we use a product rule. So another product rule can be formulated as E cross curl of E equals 1/2 gradient E squared minus E dot grad E. Same for B, so you use the same thing for B. And add a divergence of B equals 0. You've got that for free. And now we're finally going to obtain what this force is. That's a force density, force per volume. And this one we're going to write out equals epsilon naught, open bracket, div E plus E dot grad E, so that's electric plus 1 over mu naught. Same thing for B. Div B times B plus B dot grad B. And then we'll recognize this energy density, epsilon naught E squared plus B squared over mu naught. And we'll recognize this vector here, E cross B. Okay, so this will put a box around what we have to do, what our goal now is to find an object here that we operate on that delivers this back to us. This is kind of complicated, obviously. So the Maxwell stress tensor is going to be an object that when we operate on it, as we'll see what the operations are, that we get this back. Okay. Good. So yeah, this is nothing to memorize, but when we get the Maxwell stress tensor, we're going to have to make the operations on it that deliver this back to us. So let's leave this up here. And I'm just going to write down the stress tensor, and then we're going to have to start manipulating it. So let's just write down the Maxwell stress tensor. So stress is a force per unit area, so it's going to be, we're going to end up doing surface integrals with it, but that's just because of what stress means. So here we go. Tij equals epsilon naught Ei Ej. This is obviously Cartesian coordinates, minus 1/2 Kronecker delta E squared plus 1 over mu naught B sub I j minus 1/2 Kronecker delta B squared. So that's a 3x3 matrix. I goes as x, y, z, or x1, x2, x3. Kronecker delta ij, you guys know, is 1, I equals j, 0, I not equal to j. And the e squared and b squareds, we mean ex squared or e1 squared plus e2 squared plus e3 squared. Same for b. So we just go between x, y, z, x1, x2, x3 as we find it convenient. So the first thing to do is just see what some of the components are. So t sub 1, 1, or xx, epsilon naught, okay, so e sub 1, 1/2 e squared, okay, so you get a 1 right there, so you have e sub 1 squared minus 1/2 e sub 1 squared plus e sub 2 squared plus e sub 3 squared. Okay. So we can actually pull that 2 out because we've got the 1/2 we're subtracting off. So we got epsilon naught over 2 e1 squared minus e2 squared minus e3 squared. Okay. And then we'll have the same thing over here. I'll go ahead and write it out. Plus 1 over 2 u naught, same thing, same reason for the 2. e1 squared minus e2 squared minus e3 squared. And an off diagonal, I won't do all of them. For a single off diagonal, say t sub 1, 2, you've got epsilon naught E1, E2, nothing here, right? 1 over mu naught B1, B2, nothing here. E1, E2 plus 1 over mu naught B1, B2. So yeah, the off diagonals are simpler. and I'm just going to write etc. You can, for one thing, you can see this is a symmetric 3 by 3 matrix. So you don't have to get all of them to know what they are. But that's the first thing, is just to realize how to write these things out. Yeah, I have quite a few more written out here. Leave more room in your notes if you want to write more of them out. But that's how it's done. Okay, so what's next? So we have, like I just said, a symmetric 3 by 3 matrix. So I can just write Tij is a symmetric 3 by 3 matrix. And we'll do this double arrow up on top to discuss it. And it's a 3 by 3 matrix. I'm going to go ahead and write it out just to have it in front of us, right? T11, T12, 3, T21, 23, 31, 32, 33. Because what we're going to look at next is scalar product operations with this. So matrix multiplication. So next, our dot product, we can just write A dot T, but since we're multiplying an entire matrix here, I'm going to take the jth component of that, and it's just like multiplying a vector to a matrix from the left. Okay. So if I write it out as a sum, got A sub I, T sub ij, summing over I. Okay. So I'm sum over I. So this thing is labeled by J. So that's row times column. Okay. So I've got a row times a column. So if I were A dot T1, okay, then it would be the one column, which is this. So a row from the left, column there. Okay. So row times column. I'm even going to write it out since I have it right here. So the entire thing, you would be doing this matrix multiplication. A1, A2, A3 times T1, T22, T31, T32, T33. Okay, so that's what you'd have, and you'd have to do it 3 times, and you would get, so this times this tensor is a vector. Okay. Whereas that's an individual component of the vector. Okay, so the next thing, we're going to have to erase the board now. The next thing is to calculate a divergence. And again, there will be 3 of them now, instead of just 1. So next, divergence of T. And so divergence of T is again going to have a jth component, because there will be 3 of them. Sum over D dx I pi j. I equals 1 to 3. Again, you see we're doing it along a column. Okay. And that's in keeping with your formalism of multiplying from the left. Okay. Doing that along a column. i.e. divergence of the jth column. Good, so we have that. And now we can actually go back into the original matrix that we just, or tensor that we just, and in fact, why don't I just continue right here? Do the jth one, so we will have epsilon naught sum over I equals 1 to 3, and just do this on those components, d dxi ei ej minus epsilon naught 1/2. So that's the Kronecker delta d dxi e squared. And then for the magnetic part, 1 over mu naught sum over d dxi b sub I and j minus 1 over 2 mu naught delta ij d dxi b squared. Okay, so we're summing over the repeated index in each case. So let's see if we can go straight to this next expression, or we'll do an intermediate step. Yeah, let's go ahead and write it. So actually, I'm going to write these out, and then we'll point out what happened on each one. E sub j div E plus epsilon naught sum over E sub I E j xi minus epsilon naught over 2 xi e squared, and let's go ahead and put this after 1 u naught. Same thing here, b sub j div b plus epsilon naught sum over I b sub I db xj, and finally 1 over 2 mu naught d dxj b squared. So let's make sure we see what happened on each one of these. So this first one here, epsilon naught e sub j, we're differentiating the d x sub I. Okay, so that goes with the e sub I, so we pulled out an e sub j, and then we still have a sum, and that's the divergence of e. Okay, e sub 1, e sub 2, and e sub 3. Okay, so that takes care of these two. Then we have the Kronecker delta term here. Yeah, and that's a product rule. Okay, d dx of I e squared. Okay, I equals j, so you just have that. Otherwise, you're going across the whole thing, so you've got your e sub I. This is 2 cancels the 2. E sub I d e sub I dx sub j. Okay, so that gives you both of those. So yeah, all of these are now accounted for. Good. And I'm actually just going to keep going under here. So these next steps are going to bring it into the shape that we had before, or something very close. Divergence e squared. Here we go. Equals epsilon naught div ej, we have that, plus e dot grad ej minus 1/2 jth of e squared, and 1 over mu naught. Same thing with b. Sub j minus 1/2 gradient j b squared. So now we have, since that is the jth component, then if we take the entire, all 3 of these, we have the following. Now, and you have that written down, we've got the divergence, not just the jth one, but all 3 of them. And the remnant out there, epsilon naught, mu naught, you see from our pointing vector. So that is a major simplification. Okay? It's the force per unit volume is a divergence of one thing, and then this pointing vector of another. When we turn this into surface integrals, we're going to get that flux there that we had before. So, and the original force that we had is just the integral d tau over a volume. Okay, so what we have to do next is get an actual interpretation of what's going on here. So we're going to write this out. In fact, I'm just going to insert this thing into here, and we can use the integral theorems on it as well. So again, this is a force per unit volume. There was a force per unit volume over a volume integral. So, putting these all under an integral, we have the following. Yeah, we're going to write both of them down. So first of all, we'll put them both under the volume integral. So now we have the divergence of the stress tensor d volume minus epsilon naught u naught ds dt, pointing vector, over a volume. Now what we're going to do is the first one here, we're going to do Gauss's integral theorem. So directly under here, with Gauss's integral theorem, we have boundary of the volume, T, dotted into dA, or n hat d area, and here we still have epsilon naught u naught ds dt in the volume there. So this is an integral, but unlike normally having a dot product and having a scalar in there, as we just saw before, we have three components for this force, and now we can tease out what this means, because this is going to be a, force was force per volume times volume. That's going to be a force per area, and like I said before, the meaning of a stress is a force per area, the area. So good, we have this, and now we'll look at all three in d tau. Right, good. Okay. Integral d volume t dot dA. Now we need the kth component here, where k equals 1, 2, or 3. And again, this is just a matrix multiplication, so let's write it out. T11, 1, 2, 1, 3, 2, 1, T2, 2. 3, 1, 3, 2, T3, 3. And the dA sub 1, 2, and 3 as well. So yeah, we're in Cartesian coordinates right now. So again, it's row times column. So in fact, yeah, let's write it a little more. So we're going to do the z or 3 component in our problem later on. So let's go ahead and write that one out. So T dot dA 3 or z component is going to be third row times column. So T31 dA1 through 2 dA2 T33 dA3. Good, and again, this is the force, yeah, these are forces. Okay, these are forces. So let's go ahead and, to make clear what this is, I'll write it down, then I'll draw a picture. So T sub ij is equal to force per area in the ith direction acting on an element surface. So acting on an element of surface directed in the jth direction. Okay. So ith, force per area in the ith direction acting on a surface element of surface element directed in the jth direction. And the way to see this is to do a 1, 2, 3 or x, y, z axis here, and I have to draw a cube. Maybe it's better to draw the cube first. But this is how you'll see this. So let's give this a try. So we draw a cube. I gotta isolate this cube a bit more. Do it over here. Okay, cube. And corresponding axes. So, which way is the best way to do this? So, say we're in the middle here. Yeah, here we go. Okay, so this is 1, 2, and 3, right? X1, X2, X3. So good. So this is the electromagnetic force acting in the ith direction. So suppose we have T11, 1. Okay. It's acting in the ith direction on an element of surface directed in the jth direction, in this case in the same direction. So this is the 1, 1 surface, and we've got a force acting on that surface. So either in or out, acting on that surface. T11, what are we calling that? A pressure. A pressure. Now let's look at T12. Okay. So T1 is still directed in the X1 direction, but it's acting on the 2 face. Okay, which means it's a shear. Okay, right. So back to this one here was a pressure was acting in the direction of this front face here. This other one, now the force is still along this X1 axis, but it's acting on that side face. That's why the whole thing is a shear. Okay, and this is something you have in solids and in fluids. Although in fluids they don't sustain a shear, but principally you have that in all continuum systems. Okay, so T12 is a shear. I don't know how better to show that. T11 along the 1 axis, T12 shearing this 2 face. T13 would be shearing the top or the bottom face. Okay, shearing the side, shearing the top or the bottom. Okay. Don't know if there's much more to say about that. Consult the clock. Okay, great. So yeah, to go back to where we started, right, we just wanted the force on this body, and the expression was pretty major, but now it's boiled down to these very nice consolidated things. Now, if you actually have to do a calculation, an explicit calculation, you're going to have to go in and calculate everything. But there's some simplicity here when we start doing the theoretical aspect of conservation laws and things. We'll be working with these and not with all the individual constituents. So that's going to be good. Good. So the next thing is this application. And we're actually going to use this, so I'll send this up here. And back to our charged sphere. Yeah. Okay. Back to our charged sphere, and I'm just erasing this. It's a static situation. There won't be any time derivatives there. So for our charged sphere, we're going to be doing this. And I'll even say before I erase this, the charged sphere just had one component, the Z component, which is the one we wrote out right up there. Okay, so that's what we're going to be working with. So now we're doing the net force on that northern hemisphere. So returning to the net force on the northern hemisphere. So first of all, we're going to have F sub Z, or F sub 3, it'll be the surface of this dA Z, or 3. So that's what we have up there. On, I can define our surface right now. So this, if this is X, Y, Z, we have that hemisphere here. So that there is a, I don't recognize that as a hemisphere. Maybe I should do the hemisphere first. And something like that. X, Y, and Z. 1, 2, 3. Point being that there are surfaces here. There is the upper hemisphere, and it will always have a surface normal R over R, right? That'll just be R hat. And the bottom surface will be a disk. So n hat for the disk will just be equal to minus z hat. Okay. So the unit vector for these two different surfaces, we've got the disk and we've got the hemisphere proper. Okay. So I calculated this out in excruciating detail. Let's see how much we're going to put up here. So first of all, Tzx, Tzy, Tzz. Okay. So we have Tzx, Tzy, Zz. We've got the epsilon naught Ez, Ex. Epsilon naught Ez, Ey, epsilon naught over 2 minus Ex squared plus Ey squared plus Ez squared. Okay, so those are easy. Right, you've got your off diagonals and the diagonal. We had calculated one of those. And what about dA? dA for the upper part. So the upper part we have dA is just r squared sine theta d theta d phi times the unit vector r hat. And now we have to start calculating. See, we don't have any B fields here, we don't have any currents. Okay. So this is everything we have to calculate. We have to calculate E using Gauss's law. Okay. E using Gauss's law is pretty basic because it's that uniformly charged sphere. Let me make sure I have all these ingredients here. Good. So next, calculate E using Gauss. So that we remember is E